All ionic compounds start in a similar way. Every time we write an ionic compound, we're going to have the cation on the left, that's the positively charged, and then we'll have the anion on the right, that's the negatively charged ion. So every single ionic compound is going to have a cation and an anion. And we're always going to be able to separate them into these two parts. And whether or not we are talking about them in terms of a formula unit, like NaCl, or if we say the name, sodium chloride, we're always going to read them in the same order. So the positive one is going to be first, the negative one is going to be second. So you're always going to know which one is the cation and which one is the anion. The other way to remember it is that the metal that is in this metal-non-metal combination is always going to come first, and the non-metal is going to come second. So we're going to start with rules for naming binary ionic compounds, and then we'll move on from there. So this time when I'm talking about binary ionic compounds, that means I'm going to have one element, the metal, that is the cation, and I'm going to have one other element, and that's the nonmetal, and that's going to be my anion. So the great thing about naming these binary ionic compounds is that our naming rules are fairly similar to the all of the molecular compounds. They're not exactly the same, but they start out similar to molecular compounds. So just like we saw over here with sodium chloride, notice that this first element that we named, the metal, we just used the elemental symbol. So for the cation, use the elemental name. We don't modify it at all. And then for the anion, just like we did with those molecular compounds, we changed the end of the word from its regular ending to "ide." So we're going to change them the same way. The difference is that unlike with our molecular compounds, we don't use any prefixes. So we saw sodium chloride right up here where we have one Na and one Cl, and this is really an Na plus and a Cl minus, so it's really a sodium ion and a chloride ion. So notice that when we name the ions, a cation just has the name of its element and then ion. So calcium, for example, becomes a calcium 2+. So its element name is calcium, and the name of this is the calcium ion. The same thing is true with all of the ions that we have. The difference is that when we have Cl, this element name is chlorine, and when it turns into an ion, it becomes the chloride ion. So when we have cations, it becomes the element name plus ion. When we have anions, it becomes the element plus the "ide" and then ion. Okay, so let's look at a few examples of some different element names and molecular formulas. We already did sodium chloride, so let's look at a couple of other combinations. Oh, and I'm going to go ahead and pull up that ion list from our book here for a second. Okay, this is a reminder of what those elements form. So I was looking at sodium, which is Na+, Cl-, which is chloride ion, and we can see a lot of different ions in here. So let's look at a few combinations. I'm going to mostly stick with these first two columns in the periodic table, groups 1 and 2, and these groups 15, 16, and 17 for making some binary compounds for a minute. And then we'll talk about what to do with all of these other metals in just a moment. So if we look at a couple of possible combinations, we could make something like sodium oxide, right? Na has a charge of +1 and O has a charge of 2-. So if we're going to combine those, we need to be able to make a neutral combination. And so we need 2 sodiums because each one has a +1 charge to cancel out the -2 charge on the oxygen. So that makes Na2O as our formula unit. So let's try another one. Let's look at magnesium. Magnesium has a 2+ charge. Let's combine it with bromide ion, which has a -1 charge. So what kind of a formula unit will we put together here? If we have 2+ and -1, if you guessed that this means we have to have 2 of these bromides, that's true. So we would write this MgBr2. So just like with the molecular compounds, the number refers to the element that comes right before it. When we have a 1, we don't write the number there. Just like here, we don't write the number 1 to say 1 magnesium, but we do write the number 2 to say 2 bromides. And the reason why we do this and why we don't need to say, oh, here's our names, right? Sodium oxide and magnesium bromide. The reason why we don't need to use any prefixes is because sodium always has exactly the same charge, +1. And oxide always has the same charge, 2-. Same is true here. Magnesium is always +2. Bromide is always -1. So anytime I have magnesium bromide, there's no ambiguity about it. I'm always going to need 2 bromides to cancel out the +2 in the charges. So you should make sure that you go over to our list on Google Chrome here. Sorry, that's the browser I'm using. It seems to work pretty well with our book. This figure 2.20 in our book, this one, you will need to know all of these ions and their charges and their names, although that kind of comes along with it, right? And we're learning these elements anyway. So this is duplicate information. So I'm not expecting you to add extra elements in terms of, well, there's maybe a couple in here. Lanthanum is not one that was on our previous list. But most of these are all the same elements that we're already learning their names. And so learning their ion charges to go along with their names is just one additional little piece. So it's not a whole additional step. Okay, so you will need to remember those because we will continue using them. Now notice I did mention that we have that whole group of elements where they can form different charges. So mostly transition metals and post-transition metals. some can form multiple ions. For example, iron can make 2+ and can also make 3+. So if I were making compounds that involved iron and chloride ion, then depending on which iron ion I have, if I have an Fe2+, then I would need 2 chlorides in order to neutralize those charges. And if I have an Fe3+, I would have FeCl3. So when we write the formula unit, it's pretty clear which ion we're talking about, right? Because the anion tells us what the charge is on the cation. We know that this anion always has the same charge, and that's true for all of our anions. We don't have any anions with variable charges. So the anion will tell us what the charge is on the cation. So when we use a formula, that's totally okay. But what if I say iron chloride? This could mean either FeCl2 or FeCl3. So the way that we clarify that is we use Roman numerals. If we're using words to say iron chloride, we put in a Roman numeral 2, indicating that this means Fe2+, and if we mean Fe3+, we would say iron 3 chloride, and that's actually how somebody would read it aloud. If they were saying which iron compound they wanted, they wouldn't just say iron chloride, they would say iron 3 chloride or iron 2 chloride in order to be really clear. So let's practice a little bit with a few different compounds. So I'm going to write down some formulas and some names, and then we'll practice coming up with the names or the formulas, whichever one we haven't. So here's a formula. And another one. Okay, pause the video and write down the names in the compound formula units here for these 4 examples. All right, hopefully you took time to do that. Now, with this one, our cation is magnesium, and our anion is sulfide. This is always written as 2 separate words. Just like here, these are 2 separate words. The Roman numeral 3 has spaces between it as well. Over here, Al is aluminum. It comes first, so it is our cation. It has a +3 charge, so iodide, we need 3 of them, and so we would call this aluminum iodide. Over here on the right, the element cobalt has a 3+ charge here. And if I look at nitride, nitride is an N3-, so I'm going to have cobalt nitride. Potassium is K+, selenide is Se2-, and so I would have to use 2 potassiums to balance out the charge on the selenium, K2Se. Now sometimes we'll get some weird combinations of charges. Oops, sorry. So, for example, maybe we get vanadium 3+ and we're combining it with oxygen 2-. So what do we do in this kind of a situation? We still need to make a neutral compound, but it might not be totally obvious how we do this. What we want to do And what we're always doing is we're finding the least common multiple. I don't just mean any multiple, because we need the smallest combination. So we're going to find the least common multiple. And if you don't remember that specific term from long ago math, it's the number that both the 3 and the 2 can divide into in an even way, and it's the smallest one, the least common multiple. So if I think about numbers that are multiples, then one of the obvious ones will come if I multiply these two numbers together, which is 6. And since 2 and 3 are both prime numbers, this is the least common multiple. So we would need to say, all right, we're going to get to 6. So if vanadium is 3 plus and I need to get my charge to 6, I'm going to take 3 plus and I'm going to multiply it by 2 to get a plus 6. And with the O2 minus, not plus, I'm going to have a minus 2 times 3, and together those are going to get me to minus 6. And now my charges will cancel out. So that means I would need to take 2 vanadiums and 3 oxygens, only 2 vanadium ions and 3 oxide ions, and I'm going to put them together. So I'm going to indicate that I have 2 vanadiums using that subscript and 3 oxygens using that subscript. So I would have V2O3. Go ahead and try another example. If we have Zr4 plus and P3 minus. Pause the video and come up with that compound. Okay, hopefully you came up with Zr3P4 because our least common multiple this time is going to be 12. Now, all of our work so far has been on naming binary ionic compounds, but we actually have polyatomic ions too, and we need to know how they work. The great news is that naming and writing these compounds for polyatomic ions is exactly the same that we have for naming regular ions. So I'm going to pull up our table of polyatomic ions. Here it is. So this table of polyatomic ions is the same one that is in the book. It's just the book was a little more awkward for formatting for my video here. All of these ions are going to be ones that we need to know. You're going to need to know the formula and the name for all of these different ions. And notice as you scan through them that only one of them is positive. And I'm going to probably add one more cation to our list, but we'll talk about that one later. And we almost never talk about it as a polyatomic ion until we're talking about acids, so we won't worry about it here. I will post this list of polyatomic ions to the Moodle so that it's easy for you to find and to make yourself some flashcards. Now, if you are feeling like I'm giving you a lot of vocabulary all at once, I want to assure you that this is information that you are going to keep using over and over again. These ions are going to come back to us next week when we start balancing equations. We're going to see those ions. We're going to use them when we predict products of chemical reactions. We're going to use them again when we talk about types of chemical reactivity and different types of chemical reactions. We're going to use them next semester when we really start tearing apart how some of these reactions occur. You're going to keep hearing them, and the sooner you start remembering what the ion charge is, the easier it's going to be for you to identify them and for you to be able to use them seamlessly anytime you are doing something with chemistry. So this is really important information, and I want you to start memorizing these right away so that way you don't feel overwhelmed with it. as we keep going. Now, I don't expect you to instantaneously memorize them, but what I do expect you to do is I expect you to start memorizing them. So we are adding a lot of vocabulary early here in the semester, but we will not have very much more of it. So we've almost got all of the vocabulary we're going to be using for this semester. So I know it will take a while, but let's go ahead and keep working on it. All right, so let's talk about how we put together cations and anions with polyatomics. So notice that almost all of these are anions, and we're going to still build them and name them in exactly the same way. So I'm going to give you some examples here. Okay, so when we build polyatomic ions, they're mostly going to be in the cation slot. So let's say if we had something like sodium sulfite, for example. When we see the name, we need to start translating it, okay? So we need to start by identifying what is our cation and what is our anion. Sodium is nice and recognizable here, and so we recognize that that's sodium. And then sulfite, right now, you might need to go back to that list. So let's pull that up again. Sulfite, we'll find it. These aren't exactly in any particular order. Okay, well, sort of they are. I guess it's hard to say. Here's sulfite, SO3 2 minus. SO3 2 minus. Okay, so in order to make my compound neutral, I'm going to have 2 of my sodiums because they are +1 each. And I'm going to have 1 sulfite, SO3 2 minus. Oops, sorry, we don't write the ion charge when we have written the compound. Now, this is a polyatomic ion, so the whole polyatomic ion gets written in. But what about if we have a situation where we have more than one polyatomic ion? So let's look at titanium 3 hydroxide. Hopefully you can recognize that titanium 3, these go together. This means that it's Ti3+. And if you're still learning your polyatomic ions, which you probably are, then you'll switch back over and look at that table again and find hydroxide. Let's see, here's hydroxide. It is OH-. So hydroxide is OH-, and I'm going to need 3 of them because this is a +3 and this is a -1. So we indicate that with a subscript, just like we did before, but this is polyatomic. So the subscript needs to go around the whole thing. So we're going to use parentheses, and then we'll have a subscript 3 outside of the parentheses. So let's try another one. Let's try calcium phosphate. Pause the video and give this one a try. All right, hopefully you were able to find that calcium is 2+, and phosphate is PO4 3-. So we need to do that least common multiple thing. So calcium 2+ and 3-, our multiple is 6, so we're going to multiply by 3 on the calciums and 2 on the phosphates, which is going to give us a final formula unit of calcium 3, phosphate 2. Now, let's go ahead and practice writing names for a few of these as well. So for some more practice, try writing the names for NiClO2, 2. So ClO2 is the ion, and then there's 2 of them. KMnO4, ZnN3, 2. All right, pause the video and try these out. All right. Hopefully you were able to identify that this ClO2- ion is called chloride. There are 4 of those related compounds, and I'll admit I have a hard time remembering all of them, so I need to refresh on my flashcards too. Now, nickel is one of those elements that can form more than one ion, so we do need to indicate that this is nickel 2 chloride. Now, here's a tricky one. We can see that potassium is right here in the front, but we also take a look at this anion. This anion has a metal in it. Manganese is a metal. It's one of those transition metals. However, it's still a polyatomic ion. I told you that most of the elements that were in the polyatomic ions would be nonmetals, but occasionally we have some additional ones. So this would be potassium for the cation, and then this whole ion is called permanganate. Okay, here's another interesting one. N3- is the azide ion, which makes this zinc azide. Now, why did I not put a Roman numeral here by zinc? The reason is because in our table we see that zinc only forms one ion, at least according to our book, so we're sticking with it. Now, what I would like you to do for a little bit more practice when you're done with this video is to practice making some ionic compounds and naming them yourself. So look at those ion lists and come up, pick an anion, pick a cation, and figure out what combination you'd make, and then write out what the name is. And that will be good practice for this.